Nice. Okay, so Anthony, and for anybody else who wants to watch this video a little later, um, let's look at chapter 25, number 60. Nice. Okay, so I need to switch over here and go down to the questions. Number 60. A thin, okay. I think I remember this one being well, I guess I don't know. Let's work through it, but I kind of remember this one being, this looks like to me it's going to involve an integral and a tough one.
Yeah, that's actually the problem I have is the integral.
Okay, so let me get that far and set it up here. A thin, uniformly charged rod with a linear charge density of lambda. Find an expression for the electric potential at point P. Okay, so with that in mind, let me do a screen share here so you can see my camera. Let's see. Well, let me do this first in case anybody wants to share their screen later on. Let me go to my camera. Here we go. Let me then turn on the screen monitoring, Bluetooth. There we go. All right. So that should be popping up any second here. There we go. Nice. All right, so I wrote down number, chapter 25, number 60. The grid looks something like this. They have a vertical axis. They have a horizontal axis. I'll call this X. I'll call this Y. They put a charged rod line along the X-axis. I'll just kind of color that in. They say the rod has a length of L. It is actually a distance of A away from the origin on the x-axis. And the point that they are asking us to find, or the potential at the point P they're asking us to find, is a vertical distance of B. And I'll keep going. Tell me if you want me to stop, but it sounds like you did that much. It also sounds like you set up the integral right. I like to do this. Maybe a change of color would help. I always like to just kind of take kind of a random spot in there and say, let's look at that and say that that has a charge of dq, and then ask this question, what is the potential at points P from that little chunk of charge? And so the total potential, I like to start off, would be to say it's the sum of the potential from the individual points. And one of the lessons that sounds like you learned in here was that this equation, Coulomb's constant times its charge over its distance, notice not distance squared, is the equation for the potential from that point. So if we add all those up, we would get, of course, this potential at the point P. And then, of course, like all of these, this is where we have to set up a an integral that changes it from a dq to what ultimately needs to be done, and that's an integral along the x-axis. Mm-hmm. So let's see if we can change everything.
That's the
to a dx.
Charge density dx, right?
That's, pardon me?
Charge density dx.
Yeah. So you've seen that in the past chapters and starting to get used to it, that the charge density, lambda, is how much charge on a given length, okay? So if you move that to the other side, this would be lambda dx, as you just said. Same logic goes down in the bottom, that this right here is the r, and that, of course, is the hypotenuse of a triangle that's made here. And we've got different ways we could write this. I like to write it this way. I like to just think of this chunk at some distance x, and its vertical distance is b. So I could write this as an x squared, b squared, and then take the square roots.
Yeah.
Okay. Some people, like to include the a here. And of course, both are valid options. But I'm going to
put A's and the L's in
limits.
the limits. Yeah, the integral.
Yeah, right, good. And I think it looks better that way. Then, if you call that x, then you're saying you start at a, and then you keep integrating until you get to a plus l.
A plus L, yeah.
Right. Okay. Yeah, and I think that's a cleaner way because it makes the integral look the same. But of course, a change of variables, you get the same integral. So, it's one of these phrases that it's six of one, half a dozen of another.
Mm-hmm.
Okay. All right. Which, of course, again, if I'm reading into you a little deeper, you kind of made it sound like that wasn't your question. You got that far. Okay, so now we're off to do the integral. And this is Coulomb's constant times lambda. And the integral then becomes a dx, x squared over b squared to the 1/2. And of course, the limits are from a to a plus l. And let me use this as an opportunity, especially for anybody who might be picking this up later on the recording, that, and I think I said this a couple of Fridays ago, but I'll keep saying it every Friday, is that you can just look these up on the homework and on the test. Anything that's harder than a U sub. Now, in a face-to-face setting, I usually give the students the integrals that are harder than a U sub. This kind of looks like a trig sub, but because it's only a 1/2 power, I question that. So it might be something a little harder. But it's definitely not a simple power function, and it's not a U sub. So why don't we go ahead and just look it up?
Yeah.
And in fact, I'm going to go ahead then and see if this helps anyone. Let me change my screen share to my PDF. New share. Where's my PDF? PDF. Because I have the textbook here. Okay. And if you go all the way to the back of the textbook, and it's Appendix B. In fact, I just want to see if this is working. I'm going to go to my other monitor here, see what you guys see. Okay, good. And then over here on the left, you can see Appendix B, Math Review. I'm going to just click on Appendix C because if I go up a page, maybe another page, I think I'm going the wrong way. Here we go, Appendix B. This is the page I'm looking for. Oh, and I even remember it. I had pointed out to a number of times. It's table 8B. Let me make it a little bit bigger. Let's make it 100% here. But I'm pretty sure the one we want, there it is this one here. Yeah.
Yeah.
So this one says, and I'm going to just, I know my camera's not on, but I'm going to write the answer. It's a natural log of x plus the square root of x squared and why do they have plus minus?
Yeah, shouldn't it always be positive?
Um, yeah, and so maybe that's why the two are there. Let me keep going and we'll study that a little bit more. Um, probably should be careful though looking at that because uh, the A on this page here is really the B on our problem.
Yeah.
So I'm going to write it as a B because I also have an A in my problem and I don't want to mix those two. Okay. So now that I've looked that up, let me go back to share my screen with the camera here, which takes a couple steps here. There we go. All right. And so when that comes back on here, there we go. Okay. So so this integral I didn't really do. I just wrote it down, and I should also put the limits. But now that I have you on screen here, I can say, okay, so this is what you want to watch for, that you put a B there, not an A in our problem. Of course, and then our limits are from A to A plus L.
Yeah. Okay. I can
Okay.
do the plugging in.
Right. Okay. Good. Yeah. So
Yeah,
do the
I
rest
gotta,
of the.
yeah, I gotta remind myself to use that appendix.
Yeah. Yeah. Use that appendix, or Google it. In today's world, that's an option. But in the old school world, that's why you would have these reference books. And so they still make the books that way with the appendices, but I think they're used very little.
Yeah.
I had a quick question about the lab.
Yeah. Go ahead.
So for the questions, we just need to submit the 3 drawings with the fields,
Yeah.
and then only answer question 2 and not worry about question 3.
Remind me, which is question 2?
Let me hold on one sec.
Okay.
Because you said not in the video not to answer one of them. So question 2 was from the equipped potential lines, sketch the electric field lines. Be sure you understand the exact relationship between the equipped potential lines and electric field lines.
Yeah. Okay.
And then question 3 was be able to describe the nature of the electric field in region of both insulators and conductors.
Oh yeah, right. Yeah. So good. Yeah. Answer 2, not 3. That's a good way of saying it. Yeah.
Okay.
Yeah.
Cool.
Also for that lab, on number 1, you skipped the second drawing, which is of an insulator and a conductor in a field.
Yes and no.
Okay.
I thought the instructions, if I were to
You
the
could
students,
pick 3 out of the 4.
the students are allowed to draw any 3 of them.
Oh, okay. I
And
drew the other 3.
right, and if it was face to face, you get to pick your 3. But since it was me doing it, I picked the 3.
Okay.
And I thought those 3 might be the ones that would be good as a universal.
And for number 2 on the lab, I stated that the electric field will follow. The reason that they're always orthogonal is that the electric field will follow the direction of steepest descent, so to say. Is that correct?
Sure. Sure,
Yeah.
that's good.
Okay.
Once you start using ascent, you're almost talking about contour, not
Yeah.
equipotential lines. So I suppose the word gradient for you who've gone through Math 200 might be better than
Yeah.
steepest descent. Yeah.
Right.
You know what I hadn't turned on is, did I do the recording? I did.
Mhm.
Good. Did I didn't turn on my chat? If we start to get busy here, let's say throw your question into the chat so I know who was first or next in line. But at this point, anybody who wants to unmute and fire a question at me, feel free.
I'm still playing catch up on chapter 24 homework, so, but I don't have to worry
Yeah.
about math homework this weekend, so I'm hoping by the end of this weekend I'll be caught up in all my classes.
Yeah. And then, and it's normal. That's not just an online thing for this semester. That's always happens. Kind of like how the red is a little easier to see on a little screen on my desktop.
Definitely pops out.
Yeah, maybe I should do red, and if I need a different color, go to the black here. I should get one of those multicolored pens.
I use these easy erase pens.
Oh yeah,
They're friction pens, and
yeah.
I just buy a whole bunch of colors, and
Oh, and then they come in different colors, right? Okay.
yeah, so I just have a bunch of different colors and switch out pens on, like, if I need a different color or something. They're refillable too.
Yeah, I need to. Yeah, maybe I can swing by a CVS or Target or something.
And they're nice because you can erase the ink if you mess up on something. So
Yeah, there's a lot to be said about that. Yeah.
If no one's asking a question, I've got a question for you.
Oh, sure.
Okay. So let's see. I'll just share my screen again so you can see what I'm doing.
Yeah. Oh, okay. Yeah, good. Because I want to write that down too. And yours don't have numbers, but they've got a title.
Yeah, yeah. So I was actually going to show you just. I'll just pull up the thing.
Oh, I probably got to stop sharing mine though first, I think. Okay, now try it.
Okay. Screen share. Share. So this is the problem.
Okay. So it's another a 1D.
Yeah, it's another thing actually where I've found the correct answer and everything. I just have a sort of conceptual question I would like a little clarification on.
Okay. Yeah, now that I wrote it down here. Hey, I'll leave it on the screen there. I'm going to read it on my bigger screen. A ball rolls down a ramp slowly and eventually it's going up the ramp, slowing and eventually rolling back down. Its velocity is given by this equation. Okay. The ball at the bottom of the ramp, the ball is at the bottom of the ramp. That is point X equals to 0 at T equals to 0. Okay. The ball reaches a maximum position, T max. The ball reaches the bottom of the ramp on the way. Okay. I think I got a general idea. Okay.
Yeah, so I just I found my X max by using the what's the equation? The velocity position from velocity and acceleration sort of equation. X equals x naught plus v naught t plus 1/2 at squared.
Let me ask you, how'd you get that equation? Just to maybe help you out here.
How did I get that equation?
Uh-huh.
I read it out of the book. Is that
okay? And there's why I want to be a little careful. Because
I had to find acceleration using v of t equals v naught plus at.
Okay,
So I used the equation we were given, that v of t equals v naught plus at, to find a.
Okay, good.
And then once I found a, to find t. And then once I found t, I used that plugged into the x equals x naught plus v naught t plus 1/2 at squared.
Okay, now all of that is really good. I just, and maybe I'm being a little anal here, because the equation you used is correct, but that equation would only be correct for a constant constant acceleration, which is what you have in this problem. So that is correct. I guess I would have felt better if, when I said, how'd you get that for position, you would have told me I integrated the equation for velocity.
I integrated the equation for velocity. Okay.
See, because the problem we're doing does have a constant acceleration. Therefore, it comes out to that same equation that you are quoting to me.
Okay.
But had this problem been a problem of a non-constant acceleration, the equation you're quoting to me would not be valid.
Okay.
Because when you integrated the velocity one for a different looking equation, you would have gotten something very different than that equation. And so what I guess I'm just being a little, hopefully helpful here now.
No, that is
that be careful, because the one you picked is right, but there are times it may not be right. Where the integration of the velocity equation is I'll call it the fundamental principle, the principle that always works. And you get the one that you quoted if the acceleration is a constant. And that is the case in this one. So like I said, I'm being a little anal there, just to make sure that had this been a difference problem without a constant acceleration, you must have integrated, and you would have gotten something different than that equation you're quoting.
Okay. And when I integrate that velocity equation, that would give me what? That would give me the acceleration?
It would give you, no, the integration would give you position, the derivative would give you the acceleration.
Right. Okay.
Uh-huh.
Okay.
In fact, just depending on where your questions go, I'm
I
going.
see what's going on. Okay, so if I were to integrate that, I would get 1/2 AT squared.
Yes.
Okay, I
Yes.
see. I see what you're talking about there. Okay.
Okay. And so sorry, I missed. I directed you away from your question. So.
Okay. No, but that's I like that. I like making that connection. But here I'm given an acceleration, right? I'm given the A, so I'm not looking for A particularly, right? I mean,
Correct. Like I said, I think I'm learning to read these questions. See, there's not a question, but the last line.
so it wants me to find the X max and
the time on the ramp.
Yeah. So anyways, I found it using those equations that I said, but I didn't do any calculus, so that's a good thought. But I found X max to be something, and then I went through like a sort of, I used that same equation again to find T, and just found that T was just double the original time I found for it to go up and for it to go down.
Okay, perfect.
Yeah. And I was wondering, I don't know, I just wanted a little sort of conceptual thought on why that's going to be, why the acceleration. I mean, I guess if I've got constant acceleration, then something going up a ramp will come back down that ramp at the same speed it goes up it.
Yeah, that's good. I'm glad you noticed that. And so once you notice that, one way to do this problem is get to the, is just figure out the time to the top and then double it. But
yeah.
But you could have, if you didn't notice that, another alternative here is, now that you have the equation for position, set that equal to 0. Because when the ball gets back down, it's at position 0 again.
Okay.
And so take that equation that you quoted to me
and
set it equal to 0 and solve for the time when is it at 0. And of course, there'll be two solutions. One of the solutions is time itself is equal to 0. That's when it was starting on its way up. That's the one that you're going to just ignore and say, well, yeah, that's a solution, but that's not an important solution. The other one is the one that would be the time when it got back down. And then you don't have to worry about doubling the time on the way up or anything like that. And you don't have to prove to yourself that it's double the time. And that might be a little cleaner in your head.
Yeah, well, I mean, I did something along those lines before I realized, and then I realized that I just needed to double it, which was, I just did a second problem where I started with, I just knew that the distance was 9.84, so I made the position 9.8, the final position 9.84 meters, and I use the position equation again, like 9.84 equals 1/2 times the acceleration times t squared.
Okay, right, but let me show you.
Show me what you're talking about, because I'm a little confused.
Okay, let me go back over to my camera here. And while my camera's hooking up, Samson, I see that you asked a question here in the chat. Yeah, I've just invited everybody to come anytime. And I don't know if you heard me when you were here a moment ago, but I said if you had a question, ask it in the chat or unmute yourself. And so I'm going to come back to you as soon as I'm done with this one, okay, Samson? And then Daniel will get back to you, okay? All right, thumbs up. All right, so now to finish this one, let me say this is the equation you're talking about. X equals, and so when you integrate this, you get well, I'll put it here first. V naught times t for that one. This one you have the a. When you integrate it, you get t squared with the 1/2, and then the constant of integration would be what your book writes first, I think. So I'm going to write it first there. And so this is the equation you were saying.
Mm-hmm.
And then the problem goes on to say, and they give you some numbers, they say the initial position at the bottom of the ramp is 0. So I'll just, now that I put it there, cross it out. The initial speed is the 6.29 t. The acceleration is the negative 2.01 t squared. And what I was saying, a good approach on this problem would be to say, they want to know in the second part of the question, what time is it when it gets back down to its starting point? So that means its x would equal to 0. And I'll just do a little math here. This would become 1.005 t squared. So that's the physics part of it, is to say, when does it come back to its starting position? When does x equal to 0? That's the part we were talking about this morning. I said, you need to keep practicing on reading the math. You know, so when you read those words, what does that translate?
Mm-hmm.
Because once you get to this point, now it's solving the math. And so if you factor out a time, you get a math equation that says one option is time equals to 0. Another option is 6.29 minus 1.005 t equals 0. And if we continue to solve this, we get 6, let me put my calculator here, 6.29 divided by 1.005, and that barely changes it, but it changes it to a 6.26 seconds. And so what this math is saying, that there's 2 moments in time when its position is at 0. And this first one is, you know, the t equals to 0. That's when it got started. So that was on its way up. And then this is the one that they would want as the answer. This is when it, you know, rolled up, stopped, came back down, and got to x equal to 0 again.
Cool. That makes sense.
Yeah. And so that would be a little different approach. And like I said, you wouldn't have to then convince yourself that the time up and the time down is the same. And so if you just solve for the time up and double it, you'd get the right answer. Although that's true. That certainly is true. And I'm glad you saw that. And that's one way of doing the problem. But I think this might be a little cleaner way of doing the problem.
Yeah. Cool. Thank you.
All right. Hey, Samson. Can you unmute, or do you have a microphone, or you want to shoot me a question in the chat? Are you from 102? No questions right now. Okay, great. Yeah, a lot of people just want to hang out. So if that's what I was wondering earlier when I, offered you to ask a question and you didn't say anything. So yeah, just enjoy yourself, hang out. You'll see that there are mostly questions from the 122 since they're in the real hard stuff. Although now the 121 stuff are starting to ask more questions. And then once in a while, a 102 person will pop in and we'll do some 102 stuff here. All right, so let's come back up to you, Daniel. what's that first part? Oh, you were answering Samson's question. Oh, yes, they are. Okay, then when you're done, I'm having trouble on chapter 24. Okay, good. Not good that
Yeah.
you're having trouble. Number 33, I'm going to write that down. Okay, so let me then, okay, take this out of the way.
I'm just trying to figure out how to derive the formula. Once I get there, I'll be good.
Okay, so chapter 24, number 33. And I need to switch over and scroll to chapter 24. Here we go. Number 33. So 33 says a long straight metal rod of radius 5 centimeters and a charge per unit length of 30 nanocoulombs per meter. Find the electric field. And they give us 3 centimeters, and then B is 10 centimeters, and C is 100 centimeters.
I know 3 would be the 3 centimeter would be 0 because it's inside the radius.
Excellent. Okay. So if I were to draw a picture of a rod, since they said it was a metal rod, the charge is on the outside surface, and the field, as you already said, inside is 0. So A is the easier one, 0.
Mm-hmm.
Now, let me ask this question for you. Because B and C are each outside. And so the equations we tend to derive tend to be valid either inside or outside. So I would say whatever equation I'm going to derive here would be valid for both B and C.
Okay. Because they're both outside the radius.
Yeah, because they're both outside. So I'll do the quick derivation here. If you draw a Gaussian surface, maybe since it's a different color, I'll make it solid lines. But if you make a Gaussian surface that has a radius of R and a length of L, this Gaussian surface is outside. So that's why I was saying whatever I derive here is going to be valid for both B and C.
Okay.
Okay. And then so coming to Gauss's law, the integral of E dot dA would then be equal to the charge inside of the Gaussian surface over the permittivity of free space.
Okay.
All right. And
which that makes sense. That's just the regular formula. The
yeah.
Generic formula.
Yeah, and so, it's I like to make this joke. I don't know if I've done it already in class, but if you'd like to know the answer to all the homework problems in chapter 24, this is it. And the whole point of chapter 24 is to say that Gauss's law is a very powerful tool, and we can find the electric field for a lot of different scenarios. And so every problem in this chapter really is centered around this equation. So you could argue that you would start every problem in the chapter with this.
Mm-hmm.
And then, of course, the geometry is different. So when you work out the details, things come out different. And so in this case, the first thing is to take the dot product and do that symmetry argument that if you imagine yourself somewhere on this Gaussian surface, you drew a line, because this rod is infinitely up and infinitely down. And I think I've done this a few times, but I'll keep doing it. If I kind of put my fingers pointing out in the direction of the line of symmetry and I flip them, well, maybe I was using a pen. I use a pen and I point it in the direction of symmetry, and you imagine flipping this whole thing. Because all the charges flip, and you end up with the same charge distribution, you should end up with the same electric field.
Okay.
And so an electric field that was not along a line of symmetry, like maybe if I held the pin this way, see, when I flip it, the pin points in a different direction, which doesn't make physically any sense. That once you flip this and you have the same charge distribution, you should get an electric field in the same direction. And so this is our argument that this electric field would not be a valid electric field, because you flip it, you get the same charge distribution, but a different direction. That makes no sense.
Mm-hmm.
A contradiction. Same charge distribution should give you the same direction to the field. And so that's our argument, that lines of symmetry would be the directions of the fields, because when you flip those, you
It's
are still
going
pointing
in the same direction.
in the same direction.
Okay.
So knowing that, then this would be the answer to our direction. Our angle would be 0. That is, the electric field is radially outward, but then so is dA. Another part of this important piece in the argument, not really doing the math, is to say that
E is a constant?
Yeah, is to prove in yourself that it's a constant. And so if you imagine yourself standing on different parts of this Gaussian surface, like right here, you would say, well, I have an infinite amount of charge above me and below me. But if I'm here, I got that same pattern, an infinite above me and an infinite below me, the same distance away. If I'm standing here, I got an infinite above me and an infinite below me, same distance away. So my logic being here that all these 4 points on the Gaussian surface must give me the same magnitude. And so I can pull that out in front of the interval. And so those symmetry arguments don't involve much math writing here, but they do justify why I can get rid of the dot product, why I can get rid of the cosine, and why I can pull the E out in front.
Mm-hmm.
And then that means that I have a fairly easy integral to do.
Yeah, which is just A.
Yeah. And so my sticky notes that I kind of used before, this then, I would argue more from geometry than calculus. If I have a Gaussian surface that is in the shape of a cylinder, so this is supposed to be my Gaussian surface, and be these black lines out here. But if I wanted to know the area of this, I kind of imagine unrolling it and laying it flat and say, well, how would I get the area of that sticky note? And it would be its length, and so there's the L, and it would be its width, which would be the circumference when it was rolled up, and so that would be the 2 pi r.
Okay. And that's just because that's the area of a cylinder.
Yeah, exactly.
Okay.
The surface of a cylinder, to be a little more accurate. Yeah. And
do you do anything with the QN?
Yeah. So let me keep going. Let me take my sticky notes and come back and look at the picture. So the charge here is saying the charge on the inside, and the charge on the inside is on this, I'll call it the metal cylinder. It's on the metal cylinder, but it's enclosed in this Gaussian surface.
Mm-hmm.
So it would be lambda times L, because the whole meaning of this lambda is how much charge do you have per length.
Okay.
Which then is great, because now an L shows up on each side. And so I can finish the equation by moving this 2 pi downstairs with the epsilon naught, and then the lambda over r.
So the Q in what? Sorry, I'm just trying to figure out why, like, the lambda makes sense, but I don't understand why the L is there.
Oh, okay. Let me. I'll put it to the side here. Lambda means charge per length.
Mm-hmm.
Now, you could then think of it as a small amount of charge over a small amount of length. But you could also think of it as the whole charge over the whole length.
Okay.
And now if you move that L next to the lambda, so lambda times L is the charge.
Okay, that makes more sense. I thought lambda was charge over density. But
No, it's
I
charge
guess I was
over
misusing
length. Right. I see the confusion in your words. It is lambda is charge density,
that. Okay.
which means charge per, and I'll pause
Length.
because it could be length, could be area, could be volume, depending on what we're working with.
Okay, that makes a lot more sense.
So, yeah, some problems are only one dimensional, so we call them charge per length, and that's when we use the lambda.
Okay.
Some problems are two dimensional, so we call it charge per area. That's its charge density.
Okay.
And some, of course, are three dimensional, so then it's charge per volume.
Okay, that makes a lot more sense.
Good.
So for one dimension, it's length. For two dimension, it's area. For three dimension, it's volume.
Right. And
Okay.
then those are your standard symbols of lambda, sigma, and rho.
Okay.
Okay.
Okay, cool. That
All right. Good. And I see Anthony wants me to go over to number 62. Okay. Let me write that down. Oh, that's chapter 25. So 25, 62. Okay. Let me jump back to that question. So chapter 25, scrolling down here to 62. Let me take this one off. All right. And then straighten out my paper here. All right. So chapter 25, number 62. All right. So let me read it here. A solid sphere of radius r has a uniform charge density rho. That's kind of hard to read there. And total charge q. Derive an expression for the electric potential energy. And then they give us a little hint. All right. And so here's kind of the hint they're trying to say here is if you were trying to make a sphere that is charged throughout. So by the way, it would have to be an insulator because we know that charges on a conductor would all go to the surface. All right. So let's just say it's a piece of plastic. So we've got this spherical piece of plastic, and we want to get charges spread out uniformly throughout them. That's going to take some energy. And here's kind of the thinking and the hint they're given. They're saying, imagine actually building this. The first thing you might do is put a little bit of charge. I'll put a little dot for it. Then you would kind of put on the outside of it more charge. I'll just kind of color that in. And that's going to take a little bit of work, a little bit of effort, take a little bit of energy, because if these are positive charges, they would be repelling each other as you brought them in. And it would be negative too. I just, by convention, we like to draw things with positives. But then you would take another little layer. And then you would take another layer. And so what the author is saying here in the hint is to get the total energy, imagine kind of building a ball in layers, and each layer has a certain charge, so it takes a certain amount of energy each time. And you can imagine then that these bigger ones, as you get towards the full size, are going to take the most energy. I say that because of two reasons. First of all, this last one, and I'll color this one all the way in. This is the last shell that I'm going to put here. There is a lot more charge on this one than any of the other ones. In addition, I'm trying to bring it close to a lot of charge. By the time I make the ball this big, there's a lot of charge, and I'm trying to bring this close. So I would think that each little layer takes a different amount of energy, and it gets harder and harder the bigger this ball gets. All right, so the hint is calculus here. They're saying this: how much energy U does it take? And the hint they're giving is right here. Call this a du. That is, how much energy does it take to make one layer? Maybe a silly example is aluminum foil, where maybe your first piece of aluminum you crumble into a ball, then you get another piece of aluminum and you wrap that around, and then you get another piece of aluminum and you wrap that around. When I was a kid, we would do that all the time. I'm not real sure why, but we would wait around for our moms to finish up the cooking, and there would be this extra piece of aluminum foil, and we would make a little ball out of it, and when we kind of play baseball with it, and we'd wear that one out, and we'd make a new one, and it was kind of our way of getting a ball, mostly because we kept losing all the real balls we had, so we we do all kinds of silly things. Anyway, so there's just a dumb, silly story, but I'm trying to give you a visual effect of just this wrapping it together, and that's what I'm saying here. What this is, this is one layer. Maybe an onion is a better way. If you were building an onion, you would put one layer, then another layer, then another layer, and another layer. Okay. All right. So now I'm going to get into the heart of this chapter. Maybe I'll put it up here at the top. But remember, we said a energy is the charge you put there, and then the voltage or the change of voltage it took to get there. So I'm going to take advantage of that. And I'm going to do this. And then again, this takes a little bit of interpretation of the equation. This is saying how much charge are you putting at that potential? Okay, so let me use that here. Because if you kind of imagine we're building this up, this thin layer right here it's the charge on this layer, which would be here. And if this layer is thin enough, I should call that a dq. It's a little bit of charge. And so I wanted to point that out. So I'm hoping that this, this q that I have here isn't confusing you with this dq. I'm just saying it's whatever charge you put there. And then this charge I am putting right on the surface here, which is the potential created by all these other charges that have been put there earlier on. So let me just call that V for the potential that's created, not from the whole ball and not just one layer, but whatever layers I have. Okay. And so both of these are a little tricky to get. But this is where if I can use that phrase again, reading the math here is an important step here. You know, what do I mean in here? Because I think the symbols I'm using here are very different than here. In fact, you might have been tempted to put a DV and then a Q here, and that would have kind of messed up our thinking. Okay. So now I'm going to keep going. And this is where their hint is. They're saying you can think about how much charge you're placing here by remembering, and I'll put it off to the side, that density is the little bit of charge that is on here divided by the, I'm going to spell it out, volume. I don't want you to confuse the V here for volume with the V here for potential. And I'll bring my sticky pad over here and my baseball again. Because that little bit of volume in the equation would be, you know, this piece wrapped around it, either this piece of paper or this piece of aluminum foil. So if you unfold it and you say, well, okay, what is the volume of this? I would say it's the surface area, and since it's wrapped around a sphere, it's 4 pi r squared. And then the thickness of it would be this dr, that is, each layer of aluminum foil has that thickness to it. And so that's the hint the author is trying to say. Think of the amount of charge you're wrapping each time as this equation, 4 pi r squared dr. In fact, I'm going to come back over and just read that. What are they saying? Yeah, so there it is. They say, imagine the sphere is constructed by adding successive layers of concentric shells where the charge dq is 4 pi r squared dr. Oh, and then the rho. Oops, my bad. I dropped the rho. That moves to that side. Oh, and it looks like the other hint I already did. They said think of the little bit of energy for each shell to be the voltage created by the stuff underneath it plus the charge of the new shell that you're stacking on top. And so notice that I'm doing a lot of work, a lot of physics, but I really haven't done much math. And so that's why my phrase I like to use a lot about reading the math is so important here. That, you know, what do these mean? Because math-wise, I really haven't done that much. I've just written this and then this and this, a couple of steps. But conceptually and physics-wise, I've done a lot to try to know what these are. Okay, so this part, maybe I'll put a square bracket around it. That's the DQ. Now, this other part, depending on how much work you want me to do, but I think in this point, the author is saying that you can use a result that they worked out for a sphere, and they showed that the potential from a sphere is the same potential as from a point. Mm-hmm. Okay, so you're shaking your head, yes. So I think so if I just use that result here and continue on with the problem, you okay with that?
Yeah. So in their solution, they solve for Q. They solve for Q as, what did they say? It's like 4 pi r cubed over 3 times sigma.
Okay, let me.
Or not sigma, times rho, sorry.
Let me let me actually come to the solutions here. So number 25, what was it? 62? What do you?
Yeah.
Okay, so all right, so there's the potential. Okay, then you said they did something with rho. Is that what you're saying?
Yeah, they solved for Q. They said that dq is equal to rho 4 pi r squared dr, and then they plugged that into like a weird integral, like a normal integral, but it looks like it's the
Oh, okay. Wait. Um, okay, so what they did is they wrote Q in terms of rho. I see. Okay. Oh, okay. Yeah, and I agree. I'm just not there yet. Okay. I see what you're saying. Okay.
Mhm.
So let me. Okay. Right. Okay. So here's the integral. And so this first part is 4 pi r squared rho dr. I'll just change that order. But here's what you're saying. You're saying now that this Q, and here's where you have to be careful, the meaning of that Q. That Q is how much charge is underneath this new pile. So this number keeps changing. This is a something that changes with R. So for me to do this integral over dr, I need to write this in terms of
R.
Mm-hmm.
Yeah.
And so let me come to the side here. This is I think I'm finally getting to the heart of your question. Earlier on, I said rho was a little bit of charge over a little bit of volume, but rho is also all the charge over all the volume. So if you let Q represent, and I'll put this in a black color, if you let Q being all this charge that is already there as I'm wrapping the next layer on it, which is what that Q here in the equation is supposed to represent. So here's a Q. Then this volume would be 4/3 pi and whatever radius cubed we're at that moment, and it keep getting bigger. So if you move this to the other side, you have the 4/3, the pi, the r cubed, and the rho equaling that Q.
Why did they do like that integral just to confuse me?
Yeah, well, I can't answer that. Maybe you answered it. They wanted to confuse you.
Yeah, I'm gonna write down what you put real quick. Yeah. That's a much more simple way of looking at it.
Yeah. I think I think so too, and I'm not sure why they took a.
Yeah, because like I thought it was the k dq over r in the integral. I thought they were trying to do that, but then I was like, oh, but there's no k, so what's going on?
Uh-huh.
Yeah. Okay.
All right.
And then you can just
should I keep going to finish it up or?
yeah, go ahead. You just
Okay, so now, and I think personally, I think this is the harder part of all this because this is where the physics is going on. But now I've changed all the variables into r's and constants because like this 4 pi here and this 4 pi make the 16 pi squared that you see in the solutions there. This rho and this rho make the rho squared. This is the Coulomb's constant. Looks like there's a 3. And see if I'm missing any constants. I got that 4 pi. I got that rho. I got the Coulomb's constant. I got the 4. I got the 3. I got the pi. I got that rho. Okay. So now when I look at this, I've got an r squared and an r cubed. That's r to the 5. And then this just becomes r to the 4 when we divide it by 1 down there, dr. And then, of course, we're going to be adding them as we kind of imagine, starting with the first little piece of aluminum at radius 0 and going to a capital R. So this will be 16 pi squared, rho squared, Coulomb's constant over 3. And when you integrate this, you get capital R to the 5th over R5. Now, you might say technically I'm done, but there's kind of an unwritten rule that I should tell all you guys. When somebody gives a problem and says, solve it, so here's page 1, and they give you some variables in the problem, like, let me come back to read this. They gave me total charge Q, radius R, and density rho. They want to make sure your answer is in those variables. Now, I guess technically they are because I've got an R and a rho. But looking at the solution, your author did one more step here, which we can kind of argue was, not necessary. But he said, well, rho would be the total charge over the total volume. And let me just look at that, because we could then get rid of the rows and write it in terms of the Q. And that's what he does. So he goes a little bit further. But I think since they put rho in the question, we could probably stop here. But since the solution didn't, let me see if I get the same one. So let me put my 16 pi squared from here. Let me put my 3, and it's this rho squared that I'm going to use this. So this would be a q squared. This down here would then be a 4 pi squared over a 3 squared over an r3 squared. Whoa. Did I do that right? There's the 4 pi squared. There's the 3 squared. There's the r cubed squared. Okay, so that's the rho squared. Then there's the Coulomb's constant. Then there's the r to the 5th, and there's the 5. And one thing nice about that is then this 16 pi squared here cancels off. This 3 cancels with one of the other 3s and then moves up to the top. So that 3 being in the denominator of the denominator when we flip and multiply.
You can combine that with the 5 too, 3/5, right?
Yeah, so the 5 is still downstairs. Good point, over here. That 3 went up there. And then this is r to the 6th, and there's 5 of them up there, so we're left with just one of the r's downstairs.
Coulomb's
and then
constant on top.
Coulomb's constant. And then let me just check. Yeah, we got the same thing they got. Mm-hmm.
Yeah.
So they,
all right.
And I would say it looks a little nicer to finish the problem in a total charge and total radius of the charged ball versus the density of the ball. Yeah. The charge density, not mass density of the ball. Yeah.
All right.
Nice.
Thank you. I have to head off to engineering now, so I'll be back.
Oh, okay.
I'll be back.
Oh, yeah, it's that time. All right.
All right. See you later.
Okay.
Thank you.
Okay, bye. All right, let me look back at the chat. Okay, well, I don't see anything new in the chat. That's fine. Anybody out there got?
I don't know how he's doing this semester with engineering. Yeah.
Oh yeah, you started that way. Yeah.
When you said onions have layers in that one problem, I instantly thought of this scene from Shrek.
Oh.
And made it my background.
Okay. Yeah, that's right. Ah. Yeah, I saw Shrek show up in your background. I go, cool. I didn't associate it with the onion shot, though. Yeah. All right, let's see. Did I write that on there? Okay, that was 20. Okay. Well, chapter 25, number 62. Okay, good. All right. Anybody else have a question? You can either unmute and fire away or put it in the chat or. Hang out till we.
I have a
Different
question.
Yes.
I'm doing problem 35 on chapter 25. And
Chapter 25, number 35.
yeah,
Okay.
and I did the integral, but I don't get how they got, because I got ln of 1 plus L over D, but I don't know how they get L minus D ln.
Ah, okay. Let me jump back 35. 35. Where is 35? Okay. So let me build up to your integral, okay?
Yeah.
So it says here that a rod of length L lies on the x-axis with its left end at the origin. It has a non-uniform charge density, lambda L, where alpha is some positive constant. Oh, okay, so maybe I'll draw a picture, especially since you've already done this, but I need to catch up, and who knows, this might be useful to somebody later on who's watching the video. But the rod is right here. The rod is along the x-axis with the origin at the left end of it. It says it has a length of L, so there's the length of the rod. There's a point A that is a distance D away from the end of the rod, the other side of the origin. But they said that the charge density is lambda over x. And so the part you didn't ask, and you already did, it sounds like, is the units here need to work out right. So if this is supposed to come out, and we usually put brackets when we talk about units, and coulombs per meter, and this x is going to be a units of meter, this alpha needs to, number one, have a coulombs in it, so we can get that in the answer. And since this has a meter in it, but we want eventually to have one left over, there must be two of them down there. So coulombs per square meter would be the units for alpha, or like I said, anybody else who wants to do that. But that's A. Your question is along B, and it's more about the potential. Calculate the potential at A. It would look something like this. I would say, okay, so the potential is, and here's kind of the thinking process, that if you thought of a little bit of chunk of charge dq right there, the potential at point A from that little chunk of charge would be Coulomb's constant times dq over how far away it is. And that's going to be our variable, so we're going to be adding up different values of x. So this would be x plus d. All right.
Yeah.
And of course, we would be adding up then from the first location. The first chunk would be right here at x equals to 0, and we would add up until L. And so like a lot of these, we then to actually do the integral, and that's finally getting to your question, is, okay, I've got to then make everything in terms of x. The denominator is already in terms of x, but it's this charge density, which they said was equal to alpha x, and also lambda. is dq over dx, the charge per length. So if we move this to the other side, we could say dq is lambda dx, or alpha x dx. So this is alpha x dx. So I think that's where you were, right? You're shaking your head? Yeah. Okay.
Yeah.
So that's where you are. And let me give the same hint. I gave it earlier today, and I always want to give it probably every Friday. That on an exam, you can look these up. Anything that is harder than a U sub, I don't really expect you to do in the short 2 hours of a test. And of course, now that we're doing remotely, you know, and it's going to be open book, you can actually look up any of the integrals. You don't have to just look up. I mean, you could even look up the simple U sub ones, but this one's not so simple. This I think has to be done with partial fractions. At least that's what it's looking like to me. That's what it's screaming at to me. But that being said, my suggestion is go to Appendix B, go to Table B5, and look it up. So I'm going to change my screen share here and go to the textbook, which should be here. And I'm going to turn my textbook to Appendix B, and I'm going to check on my other monitor to see if it changed. Oh, good, it just changed. Now I need to scan this for a while, but it looks like it is right on the top of my screen right here. That would be it. Highlight it. See how there's an X in the numerator, and then there is a constant, and then an X in the denominator.
Yeah. Okay.
And see how it has two terms? That right there, that's a dead giveaway to me that the solution here is they broke this into a partial sum. Let me not do all the math, but you might remember in your math class that you could change this into some number with this denominator plus some number with this denominator. Bad choice. Well, it would be what it'd be multiplied by 1. And then if you integrate those would be easy integrals to do. So maybe I should ask, I could break it apart and go through a bunch of math for you, but
I remember partial fractions.
Okay, good. Partial. Yeah, partial fractions. I keep saying partial sums. So I don't know, but it's really partial fractions. So the step then would be to say.
Can you share? Because I'm seeing just the.
Oh yeah, I'm sorry. Yeah, I got to share it back to my camera again. Okay, so share. Before I leave though. Wait. Yeah, before I leave, I better write down what that integral is. So it is. Looks like it would be x over, and on the table it says x over b, but that b, as I look in there, would be the coefficient in front of the x in the denominator, so that's 1.
Yeah.
Okay. Then minus, and then it says a, and that a would be the d in my problem, over b squared, and my b would be a 1. And then it would be the natural log of the a, which would be the d in my problem, and then the x. Okay, so let me write that down. Okay, so now I'll switch back over to my camera. Now that I wrote it down, and I've got to turn on my screen sharing. Let that connect. Okay. So when I left the camera, I had this, and I looked it up. This is what it said it was.
Yeah.
And then I got to put my limits. Oh yeah, I was doing this partial fraction, and you couldn't see all that. Well, just as well. Okay, but the limits were 0 to L, so then this would be 0 to L. So then, continuing on, this would be Coulomb's constant alpha. And so if I put in an L, I get L minus D natural log of D plus L. Then it would be minus, when I put in a 0, so if I'll just put it for completeness, minus 0, and then minus a minus, so that's a plus, D ln, and if I put in a 0, that's just a D. Now this can be simplified a little bit. Remember some of our properties of logarithms. I'll put these two together, so that's just an L. But these are a natural log. This is a plus and this is a minus. When you have a subtracting them,
You can divide.
yeah, you can treat it as a quotient. So this would be ln of D over D plus L. And I think that's the best we can do. Let me see the solution. What was this, number 35? 35's got the Coulomb's constant, the alpha, the L minus. Oh, and they wrote it a little different. Instead of putting a plus, they put a minus. So let me write it their way. Well, so what they did is they took this plus and they thought of it as a minus times a minus.
Okay.
So the first minus they leave there, but another property of logarithms is anything that's out and in front here can be moved to the power. So this would be D to the ln, and this would be D over D plus L to the -1 power. So then it looks like they do then one more step. They've got the minus D, and they took the reciprocal of that, and so they've got ln, and they got the D plus L over AD. Oh, then they did one more step. Okay, then they took Coulomb's constant alpha, they got the L minus the D, and then they broke this into the two fractions, because D over D would be 1, and then you would the L over D for the second fraction. And so they undid the common denominator to.
Yeah. Okay, yeah.
I personally like that better, but
Okay.
they're the same thing.
Yeah. And also have another question for 39.
39?
Yeah, on A. When they're calculating the potential for A, they wrote that R. It's
Oh, did they
0.
put 14?
Yeah.
Yeah, that's correct and a little confusing.
Okay.
All right, let me try to explain.
Uh-huh.
Okay, so let me move this out of the way. So okay, so chapter 25, number 39, and the problem says, as you are pointing out, It says a spherical conductor of radius 14. Okay, so here is my conductor. I'll maybe put over here a radius of 14 centimeters. Okay. It has a charge of 26 microcoulombs. Now, here's a very important part of this problem. They said a conductor. So that tells me all the charge is on the surface.
Mhm.
Okay. Now, since they said it was spherical, and this would go back a chapter, Gauss's law, and I'll repeat it if you want, but I feel like you know the answer, that the electric field on the outside is the same equation as a point.
Yeah.
And the electric field on the inside is equal to 0.
Mhm. Yeah.
Okay, so getting into this chapter, the definition of the change in potential is adding up the electric field over some position. And so here's kind of the key that they're getting at in this one, and really the heart of your question is when you're outside, and so let's say you're over here, and you're getting closer and closer and closer and closer and closer, but you're still outside. The electric field is this, the same as a point. So the equation you would get for the potential would come out to be the same equation for a point, okay?
Yeah.
However, here's where it gets a little different than a point. Once we get to the surface of the sphere, that's the 14 centimeters, we now get inside, and as we continue to do this integral, because we would have to do this integral all the way to 10, because they want to know what's the potential at 10. So we would still have to integrate from 14 to 10. But that integral would look like this. The field would be 0 times dr as we go from 14 to 10.
Mm-hmm.
And so the key to this problem is to realize that when you get inside, the potential will not change because the field is 0.
Oh, okay.
So whatever the potential is on the surface is also the potential anywhere and everywhere inside.
Okay.
So that's why they used the 14, even though they're trying to find the potential at 10.
Okay. So every time the electric field is 0, the potential will not change?
Yeah, so again,
Okay.
this is probably what you're really asking about. The definition of the potential is really how much work it takes as you're pushing in. So once you get to a spot where the field is 0, it doesn't take any more work.
Okay.
So on the outside, as we're trying to move a charge in, it takes work, and the potential gets higher and higher and higher and higher and higher and higher and higher. But once we get inside, it doesn't take any more work, so the potential never increases.
Yeah.
Or decreases. It just stays the same. And that's what this integral would say. If you ever had a place where the electric field is 0, then the change in potential would be 0. So from a position on the surface at 14 to a position somewhere deep inside like 10, or even all the way to the center, it doesn't matter where you go, as long as you're on the inside, you're just integrating 0.
Yeah.
Which just gives you 0.
Yeah, that makes sense. Yeah.
But it's confusing, I know, and I'm glad you asked. That's why you asked, because why would somebody use this 14? It almost looks like they made a mistake.
Yeah, I was thinking it was a typo.
Yep, no, glad you asked, because it's not a typo. It's actually the whole purpose of the problem, yeah.
Yeah. Thank you.
Mm-hmm. All right, let's see. Shall I jump back over here to the chat room? How are we on time also here? Daniel, is there still time? All right, yeah, there's time. Why not? You got another one in here. You already shot it. And let's see, number 39 in chapter 24. All right, so 24, 39. Let me come to the questions. Let's see, which chapter was I in? Oh, that's 25. So let me go back to chapter 24, 39. Okay. I forgot who asked this already. Was this Daniel?
Yeah.
Yeah, okay. Yeah, I guess it doesn't matter who asked it. Y'all can listen. So chapter 24, number 39. It says this: a long straight wire is then surrounded by a hollow metal cylinder. Okay, so I'm going to try and draw a picture here. This might be this long wire. So a long straight wire is then surrounded by a hollow metal cylinder. So maybe I'll try to draw. Oh, now I wish I had your erasable pens, Daniel, because I want to, it would look better if I can get rid of that line right there and right there. But hopefully it still looks like 3 dimensions here.
Yeah, it does.
Okay, good. All right. So there's my hollow cylinder whose axis corresponds with that of the wire. Okay, that's how I drew it. The wire has a charge per unit length, so the one on the inside, of lambda, and the cylinder has a charge per unit length of 2 lambda. Okay, so they're both charged. From this information and from Gauss's law, find, and so here's A, the charge per unit length on the inner and the outer surfaces of the cylinder. Okay, now let me also draw below it kind of a cross-sectional view. So here's the wire, then there's some empty space, and then here is the hollow cylinder on the outside. But what's absolutely important in this problem is the fact that they said it was a hollow metal cylinder.
Okay.
So we know that the field inside the metal is 0.
Yeah.
This is why that's important right here. So this wire on the inside, I'll put a bunch of pluses. And the field, if I do that in a different color, would come out.
And that would be 0 because it's on the inside of the sphere.
Now, you say it, I want to be careful. Where I'm drawing right now is not 0. But inside the wire would be 0. And also inside of this metal piece right here. And so what that tells me is negative charges must be pulled inward to the inner surface, and they can be. That's why it's a conductor. That's why a conductor can have no field inside, because the charges can shift around, and they can shift around in such a way that they can terminate the field. So this would terminate the field, and I would need enough charges on this inner surface of the outer conductor to exactly terminate the field that was created by the inner wire. So that tells me that this inner surface must have a charge density of negative lambda.
Okay. And that, so it's negative because the negatives are being pulled inwards.
Right, and the negatives are used to terminate the field.
Okay.
Now, I should also be careful. They just said the charge density was lambda, and technically, mathematically, that could be a negative number. So what I'm really saying is it is the opposite of lambda.
Okay.
So if lambda is positive, these charges would be negative. If lambda is negative, then these charges are positive. So I'm really saying that the charge density is the opposite of lambda.
Okay.
I don't really know in this problem whether lambda is positive or negative, but assuming, because that's how I drew my picture, they're positive, then the inner surface would be negative. I just know they have to be opposite.
Okay.
Okay. So with that in mind, keep in mind earlier on in the problem, we said that the whole charge density has to be 2 lambda on this whole cylinder. And again, it's a conductor, so the charges can only be on the surfaces. And so we just answered what was on the inner surface. Like maybe I should have said this is inner.
And on the outer, it'd be positive lambda?
Well, positive 3 lambda.
Oh, because it needs to be 2.
Yeah, the whole thing needs to be a positive 2 after I do everything on the cylinder.
Okay.
If the cylinder was neutral, then it would be what you said. It would be a positive.
Okay.
All right.
So that's part A.
Yeah, that's part A. Now, I think
Okay.
the harder one is the electric field inside the cylinder, a distance r from the axis.
Well, if it's a distance r from the axis, isn't the lambda the total amount of lambda needed?
So they're talking about this area, I believe.
Oh, okay.
And so the only thing inside of that is lambda.
Okay.
And I did it a problem ago. I could do it again, but I'm going to just put the results that we got a little earlier, where this lambda represented what was inside, and in this case is lambda. It's not a 3 lambda, it's not a 2 lambda, it's not a negative lambda, it's only a lambda.
Okay. The answer.
Maybe should I check the answer here?
The answer says it's a 2 coulombs times 3 lambda.
Okay, let me look. I might have read the problem wrong. I read it kind of quickly here. Let me come back to it says the electric. I did read it wrong. Outside. My apologies. Let me try it again.
So is that the total of everything outside?
Yeah. So my outside would be this.
Okay. And in order to get out there, you need 3 lambda.
Right, and so it's everything inside, which is the 1 and the 2. I'll just write it as 1 plus 2. Yeah. And so it's 3 lambda.
Okay. But so the last thing I'm confused about on that is why there's 2 coulombs constants.
Yeah. Let me look at that. Answer. So this would be chapter 24.
Oh, I see what they did. They just moved the 2 coulombs constant. Wait, isn't there a 2 in the formula for coulombs constant?
39.
Oh, okay, I see.
Yeah,
So,
I don't see 2 coulombs constant.
okay, yeah, I misread that. That makes a lot more sense.
Oh, I do see though that they got here by saying this could also be written as 2 times Coulomb's constant lambda over r. So then they replace this with the 3 lambda, and then they replace this with the 1 over 4 pi epsilon and got to here.
Oh, I see. Okay.
Yeah, so they started with a slightly different formula than what I must have derived. But I thought a few problems ago I derived it. I guess what I'm trying to say is my 1 over 2 pi epsilon naught is the same as 2 times Coulomb's constant. So we could write it this way or that way. And they chose to write it this way, but to finish the problem, writing it this way.
That makes more sense.
Yeah, interesting.
Then your next section is at 12:30.
Oh yeah. So let's take our 11:30 break here, and then we'll come back and we'll start up again at 12:30. Like there was a couple people who joined the discussions here, but we're heading off to break time, Mark and Armando. So we'll be back in 45 minutes here. Get something to eat and go to the restroom.
Sounds good.
All right.
All right, bye.
Bye now.